Welcome, everyone. Have you ever faced a problem where finding the perfect solution seemed impossible, or took way too much effort? Think about trying to pack a suitcase just right for maximum space, or planning the most efficient delivery route for hundreds of packages. When these problems get really complicated, finding the absolute best answer can be computationally overwhelming. That's exactly where semi-definite programming relaxation shines. It's a brilliant technique that helps us tackle these incredibly tough optimization challenges. Instead of chasing the elusive perfect solution, we relax some constraints to find a toughery, very good approximate solution that's much easier to compute. It's like finding a super effective shortcut when the direct path is blocked. Today, we'll explore the core ideas behind this powerful mathematical tool. You'll gain a high-level understanding of what it is, why it's so useful in fields like bioinformatics and computer science, and how it helps us turn seemingly intractable problems into solvable ones. Ready to unlock some serious problem-solving power? Let's dive in. Alright, so with those introductions out of the way, let's dive right into our topic. To truly understand where semi-definite programming relaxation fits in, we first need to discuss the broader landscape of problem-solving strategies, especially when tackling challenging nitrogen monophosphide hard problems. As you can see, this slide is titled Problem-Solving Strategies. It explores the many different methods we can use to tackle nitrogen monophosphide hard problems. And believe me, there are quite a few. These methods include, first up, we have branch and bound, or B&B. This is a very general, powerful technique for finding optimal solutions to various optimization problems. Secondly, there's dashed meta-heuristic search. A prime example here is the genetic algorithm, which many of you might already be familiar with. Third, we look at statistical learning approaches, such as expectation maximization and Gibbs sampling. Truly fascinating techniques. Fourth on our list are fixed parameter algorithms. And finally, a very important category for us, approximation algorithms. This broad area itself encompasses several distinctions. We have deterministic methods, randomized approaches, and of course relaxation methods, which is precisely where semi-definite programming relaxation will ultimately find its home. Within this category, we also consider polynomial time approximation schemes, or PTAS. Oh, and just a quick note on the visual side. You'll see on the right of the slide an image of a baby lying on a striped blanket. Just a little something there. Having just reviewed various powerful problem-solving strategies, including approximation and relaxation methods for nitrogen monophosphide hard problems, let's now build on that foundation. In fact, in past weeks, we've already explored the fascinating connection between algorithms and probability. But for today, we're shifting gears to reveal a crucial relationship, how algorithms intricately connect with linear algebra. And perhaps most interestingly, we'll be introducing you to what we call a more relaxed technique, a powerful approach that simplifies complex problems. So tying into our discussion of a more relaxed technique, this slide dives right into the max-cut problem. You might recall we've already explored several algorithms for solving it, including both a randomized to-approximation and a deterministic to-approximation algorithm. But now we're going to pose a critical new question. Can the max-cut problem actually be solved using a linear programming relaxation dive technique? Take a look at the image on the right. It visually represents a graph, clearly showing the nodes and edges, along with a line demonstrating a potential cut right within that graph. So to answer that question about linear programming relaxation, one powerful approach involves formulating maxcut as an integer program. This slide precisely presents that integer programming formulation for the maxcut problem. The fundamental idea is that we can find the maxcut solution by solving the following integer program. Our primary objective here is to maximize the total sum of y_ij for all edges i, j in our graph. What is y_ij? This variable is simply defined to be 1 if an edge crosses the cut and 0 otherwise. We want to maximize those edges crossing. This maximization, however, is subject to three crucial constraints. First, for every single vertex I, its corresponding variable x_i must belong strictly to the set -1, 1. These x_i variables are key. They essentially assign each vertex to one of two distinct partitions. Think of it like assigning each vertex a side of the cut. Second, for every edge ij, we have y_i, j must be less than or equal to 1-x_i plus x_j /2 . And third, also for every edge ij, y_ij must be less than or equal to 1 plus x_i plus x_j /2 . These last two constraints might look a bit complex, but they serve a vital purpose. They work together to ensure that y_ij can only actually take a value of 1 if x_i and x_j have different ℾ signs. This means vertices I and j are, in fact, in different partitions, and thus the edge I genuinely crosses our cut. Conversely, if x_i and x_j happen to have the same sign, y_ij will be effectively forced to 0. Therefore, by maximizing the sum of all y_ij variables, we are truly maximizing the total number of edges crossing the cut. Having just explored the integer programming formulation for maxcut, you might be wondering how we actually solve such complex problems. This brings us to a powerful technique, linear programming relaxation for maxcut. The core idea here is that we relax our original integer program into a problem with linear constraints, which we can then solve as a standard linear program. This approach immediately brings up a couple of critical questions, doesn't it? First, can this relaxation be applied to *NE's problem? And second, what exactly does the optimal solution we get from this linear program tell us? So let's dive into the mathematical formulation for this relaxed problem. Our objective remains the same. We want to maximize the sum of y_ij, or y sub ij, for every edge I gemendine in our set E. This maximization, however, is now subject to slightly modified constraints. First, for every vertex I, our variable x_i, x sub I, must now be a real number between -1 and +1, inclusive. This is the key difference from the integer program, where x_i could only be -1 or 1. Next, for every edge ij, we still have those same two important constraints on y_ij. The first states that y_ij must be less than or equal to 1 minus the quantity x_i plus x_j, all divided by 2. And the second constraint for y_ij is that it must be less than or equal to 1 plus the quantity x_i plus x_j, all divided by 2. So we've just explored the mathematical formulation for linear programming, or LP, relaxation. However, it's crucial to understand a common issue that often arises with this approach. As a reminder, the core idea of LP relaxation is to relax integrality constraints, allowing variables to take on fractional values. For example, our x sub I variables, which we just saw, can now range anywhere between -1 and +1, inclusive. But here's the significant problem. It's frequently the case that simply setting every single x sub I to 0 actually provides an optimal solution for the relaxed linear programming problem. What does this imply? Well, while this LP solution is indeed mathematically optimal for the relaxed MER problem, it becomes entirely uninformative for the original problem we're trying to solve. It offers no meaningful insights or a useful approximation, rendering it effectively useless for our true goal. Building on our previous discussion about the challenges sometimes encountered with linear programming relaxation, this slide will now clarify the fundamental concept itself, illustrating it as a powerful, cyclic process used in optimization. So, what exactly is linear programming relaxation? At the heart of it, we start with an asterisk integer linear program, or ILP. This is our initial, often complex problem where times all variables are strictly required to be whole numbers. And that integer constraint? It's what makes them incredibly challenging to solve directly. Now, the very first step in our cycle is relaxation. We essentially transform that tough ILP into a standard linear program. How? By simply removing those pesky integer constraints. This allows variables to take on any fractional value. And crucially, this relaxed problem becomes significantly easier to solve. What next? We then employ a powerful solver. This tool efficiently finds the optimal solution for our newly relaxed linear program. The outcome? Typically, a contractional solution in Mach, meaning some variables might end up with non-integer values, a decimal for instance. But we need whole numbers for our real-world problem, right? So to obtain an asterisk applicable result, we then apply a crucial step, num-dot rounding. This technique converts that fractional solution back into an asterisk integral solution, dumb and tied, guaranteeing all variables are whole numbers again. This is absolutely essential for most practical applications we're trying to solve. Finally, this newly rounded integral solution serves as an asterisk approximation asterisk for our original, tough-to-solve integer linear program. While it might not be the exact optimal solution to the original ILP, it consistently provides a feasible and, very often, an extremely good practical answer. So this entire cycle vividly demonstrates the power of linear programming relaxation. It beautifully shows how we can leverage the incredible efficiency of standard linear programming solvers to find effective, approximate solutions for even the most complex integer problems. Now that we understand the concept of linear programming relaxation and its application, let's delve into the fascinating history behind these powerful relaxation techniques, highlighting two truly significant milestones. Let's start with 1979, when Leonid Kachedyan developed a polynomial time algorithm for linear programming. This was a truly foundational step, directly paving the way for the development and widespread adoption of LP relaxation techniques we just discussed. Then, moving forward to 1994, we see another monumental leap. Yuri Nesterov and Arkady Nemirovsky introduced their groundbreaking interior point polynomial algorithms for convex programming. Their remarkable work demonstrated that semi-definite programming, or SDP, could be solved in nearly polynomial time. This, in turn, beautifully paved the way for the emergence and application of SDP relaxation techniques. Polished current slide voiceover transcript. To truly understand SDP relaxation techniques, which we just touched upon, let's first briefly review some essential linear algebra concepts. We'll be focusing specifically on positive semi-definite matrices. First, let's define what a positive semi-definite matrix is. A symmetric times n times bi times n times matrix asterisk A time is defined as positive semi-definite if, and only if, times x times transpose asterisk A times x times is greater than or equal to 0 for every vector times x times in times x to the power of asterisk n times. Simple enough, right? Now here are the really key ideas you need to grasp about these matrices. Crucially, for any matrix times B dies, the product times B dimes transpose times B dies will always result in a positive semi-definite matrix asterisk A, E-tied. And conversely, any positive semi-definite matrix asterisk A times can be decomposed into the form times B dimes transpose times B dimes. This is achieved using what's known as the Cholesky decomposition, a process that typically has a computational complexity of order n cos cubed. Moving from theoretical foundations, let's now dive into what truly became a seminal paper in the field of approximation algorithms. For a long time, the two-approximation algorithm was actually the best-known approach for challenging problems like max cut. However, that all changed dramatically with a groundbreaking contribution by M. Gomans and D. Williamson, published at ACMSTOC in 1994. What did they do? They introduced a randomized approximation algorithm specifically for MAXCUT, achieving an impressive ratio of 1 over 0.878. This translates to approximately a 1.138952 approximation. Think about that. It was a truly significant improvement that fundamentally redefined the state of the art. And here you can see the brilliant minds behind this breakthrough. M. Gomans is on the left, and D. Williamson is on the right. So how exactly is the MAXCUT problem, which we just highlighted, formulated mathematically? This slide introduces its representation as an integer quadratic program within the context of a graph problem. We begin by defining a crucial variable, _a underscore ij _. This variable is simply set to 1 if an edge exists between nodes, _x underscore I _ and _x underscore j _ and 0 otherwise. Now, what exactly are we trying to maximize? Our objective is to sum over all pairs I less than j . The term a underscore ij multiplied by 1-x underscore ix underscore j divided by 2. This mathematical term 1x underscore ix underscore j /2 is absolutely key. It cleverly evaluates to 1 if x underscore I and x underscore j have different values, and 0 if they have the same value. Thus, our objective function beautifully aims to maximize the number of existing edges where the connected nodes have different assigned values, precisely what we want for MAXCUT. Of course, this maximization isn't unconstrained. Each variable, x underscore I must take a value from the set -1, 1 for all I from 1 to n . To make this a bit more concrete, take a look at the simple graph example provided below the formulas. Here, node x1 is connected to x2 x3 and x4 . Each of these nodes represents an x underscore I variable that would be assigned either a -1 or a 1, according to the problem's constraints. This is the precise setup for solving MaxCut. Given the challenging nature of integer quadratic programming problems we just discussed, we often turn to approximation methods, and that's exactly what this slide illustrates, the process of semi-definite programming relaxation. As you can see on the left, we start with our times integer quadratic programming asterisk problem. To make this problem more tractable, that is, easier to solve, we first relax the integer constraint. This crucial step transforms our problem into a time vector relaxation asterisk problem, which is then further time reformed asterisk into a standard semi-definite programming asterisk problem. Now, here's the advantage. Semi-definite programming asterisk problems are highly efficient to solve. We can leverage an existing SDP solver asterisk to quickly obtain an SDP solution. From this SDP solution, we then apply Jom-Chalsterisky decomposition to obtain a Jom-Tom vector solution. Finally, to get back to our original integer domain, we use times randomized rounding asterisk on this vector solution. This last step helps us derive an integral solution no zeta. This entire process you see here forms an approximation method. It's a powerful loop that ultimately provides a high-quality, approximate solution to our original, challenging integer quadratic programming problem. As we discussed, a crucial step in our process is the Nye vector relaxation. Let's now explore what this entails in more detail. At its heart, vector relaxation begins by relaxing the integer constraint on each variable, x underscore I, Instead of being a discrete integer, each x underscore I is transformed into a unit length vector, v underscore I in "n" dimensions. This means each "v_i" must have a norm of 1. This relaxation is formalized by the optimization problem you see here. We aim to maximize the sum over all "i" less than "j" of "a_ij" multiplied by the term "1-v_i.v_j/2". The critical part, as mentioned, is that every "v_i" must be a unit vector. To give you a conceptual understanding, the small network diagram on the right illustrates the kind of structure we might be relaxing. For instance, a central node connected to "x2", "x3", and "x4". Essentially, the core idea is to map these original vertices to points on a unit sphere. You can see this visually represented by the 3D sphere at the bottom of the slide. This clever mapping helps to push adjacent vertices away from each other on the sphere. This is a powerful technique commonly employed in various optimization problems, especially those involving graph partitioning or clustering, where separating related elements is key. So how do we translate this vector relaxation into a problem we can effectively solve? This slide details its powerful semi-definite programming formulation. We begin by reiterating the optimization problem we just saw. Our aim is to maximize the sum over all "i" less than "j" of "a_ij" multiplied by "1 v_i" dot "v_j" all divided by 2. Recall, the key constraints are that the norm of each vector "v_i" must be exactly 1, meaning "v_i" resides on the unit sphere in "n" dimensions for "i" from 1 to "n". The small graph on the right still visually represents this, illustrating how variables like "x1", "x2", "x3", and "x4" conceptually represent nodes in a network structure. To move towards a more tractable form, we then transform this problem. Follow the red arrow, which highlights this pivotal step. We introduce a new matrix, "x", defined as the outer product of our vector collection v_1, v_2, v_n, with itself. This elegant transformation means each element x_ij in this matrix x is simply the dot product v_i v_j just as you can see demonstrated in the example matrix for x. With this crucial transformation, our original problem is beautifully reformulated into a semi-definite program. We now aim to maximize the Frobenius inner product of a specially constructed matrix C with our new matrix X. This powerful reformulation comes with two new essential constraints. X must be positive semi-definite, a defining characteristic of SDPs, and all its diagonal elements x_2 must be exactly equal to 1. The specific structure of matrix C for this formulation is also conveniently provided on the right for your reference. To fully understand the reformulated problem we just discussed, particularly that Frobenius inner product, let's take a moment for some essential linear algebra background. This slide covers those crucial definitions. First, we define the inner product of matrices A and B. As shown, it's calculated by simply summing the product of their corresponding elements, A_ij and B_ij, across all rows sprows I and columns j. This is exactly the Frobenius inner product we're using. Second, we'll introduce semi-definite programming, or SDP. This is a powerful type of optimization problem, similar to both integer programming and linear programming. However, the key distinction is that both the objective and constraint functions are expressed in a very specific, semidefinite form. Building on our introduction to semidefinite programming, let's now look at its detailed mathematical formulation. On the left, we see its mathematical structure. The core objective is always to minimize the inner product of a given matrix C and our variable matrix Y, often written simply as C.Y. This minimization is subject to three crucial types of constraints. First, the inner product of specific matrices, A sub j, and Y, must be greater than or equal to a scalar A sub j. Second, Y itself must be a positive semidefinite matrix, which is denoted as Y greater than or equal to 0. And finally, the diagonal elements of y sub 2 are typically set to 1 for all relevant indices. To illustrate what a solution looks like, an arrow points to the right, showcasing an example of an SDP solution, which is the matrix Y itself. As you can see, this matrix is symmetric and filled with various numerical values like 1, 0.2, 13, and minus 0.5, representing the computed entries of our solution. And here's a truly crucial point, highlighted at the bottom. Semi-definite programming problems can be solved remarkably efficiently by algorithms, specifically in almost polynomial time. This is a significant advantage. Now that we've explored the fundamentals of semi-definite programming and its efficient solvability, let's delve into one of its powerful applications, semi-definite programming relaxation. This technique is specifically designed to approximate solutions for complex problems, such as integer quadratic programming. So how does this process unfold? We begin with an integer quadratic programming problem. To address its inherent difficulty, we first strategically relax its integer constraint, transforming it into a vector relaxation problem. This vector problem is then cleverly reformulated into a semi-definite programming problem. Here's where the real advantage comes in. The powerful existing semi-definite programming solvers, which we discussed previously, can efficiently solve this reformulated problem, yielding an SDP solution. From this SDP solution, we then apply a technique like Cholesky decomposition to obtain a vector solution. Finally, this vector solution is processed to derive an integral solution, providing an approximate answer to the original, challenging, integer quadratic programming problem. This entire flow truly demonstrates how semi-definite programming can be leveraged to effectively tackle complex integer optimization challenges. And speaking of those powerful semi-definite programming solvers we just discussed, this slide, aptly titled SDP Solvers, highlights two important resources for you. First up, sdpa.sourceforge.net, which offers direct access to the well-known SDPA solver. It's a fantastic tool. Then we have a second link, sourced from the National University of Singapore's Mathematics Department, pointing to an alternative, equally valuable SDP solver resource. These links are truly essential for anyone looking to implement or effectively utilize SDP solvers in their own projects. Be sure to check them out. Now that we've explored resources for SDP solvers, let's dive into what a semi-definite programming problem, or SDP, actually entails and how it's solved. As the flowchart at the top illustrates, we begin with a semi-definite programming formulation and then derive an SDP solution. On the left, we see the structure of a semi-definite program. Its objective is to minimize the inner product of matrix C and matrix X. This minimization is subject to several key constraints. First, the inner product of matrix A sub j and X must be greater than or equal to scalar A sub j. Secondly, the matrix X itself must be positive semi-definite. And crucially, its diagonal elements, X sub 2, must all be equal to 1 for all I from 1 to n. Following the arrow to the right, we then arrive at the SDP solution. An example of this solution matrix, X, is provided here. Notice how this matrix is symmetric and, importantly, has ones along its main diagonal, just as required by our constraints. Finally, at the bottom of the slide, we highlight some key aspects of actually solving these problems. The SDP problem can be solved quite efficiently, often in nearly polynomial time, using powerful algorithms like the interior point method. The ultimate result of this process is the SDP solution matrix, represented as X in our example, though you might also see it denoted as y in other contexts. Following up on our SDP solution matrix, X, from the previous slide, this slide now illustrates the crucial concept of asterisk decomposition, specifically how we derive individual tie-vector solutions directly from that semi-definite solution. At the top, the flowchart clearly depicts this transformation, from a semi-definite solution to a vector solution. On the left, under SDP solution, you can see our familiar matrix X. This is, of course, our semi-definite solution. Take a moment to notice its structure. It's a symmetric matrix with ones precisely along the main diagonal and various off-diagonal values. For instance, you might see 0.213 or even minus 0.5. Following the arrow to the right, we then arrive at the vector solution. This is where the magic of decomposition happens. Our matrix X is now transformed into individual vectors, like V1 and Vm. Each vector, as you can see, is simply a list of numerical components. For example, V1 could be 0.12, 0.04, and so on, up to 0.1, while Vm might be 0.09, 0.1, and so on, up to 0.14. Now, looking at the bottom, two key points concisely explain this entire transformation. First, we need to recall a fundamental relationship. The matrix X itself is the product of the matrix formed by vectors V1 through Vm and its own transpose. Second, and this is absolutely crucial for generating these vectors, we leverage a powerful technique called the Chaykat-Julian-Strongke decomposition method to obtain these individual vector solutions, V1 all the way through Vm, directly from our original matrix X. Now that we've successfully used Cholesky decomposition to derive our vector solutions, this next slide, aptly titled Rounding, dives into the subsequent critical stage in our process. Looking at the top of the slide, you'll see a conceptual flow illustrating the transformation from a vector solution to an integral solution. On the left, under Vector Solution, we're presented with examples of those vector components we just obtained. They're fractional. For instance, V sub 1 shows components like 0.12, 0.04, and so on, up to 0.1. Similarly, V sub m displays components such as 0.09, 0.1, and 0.14. As you can clearly see, these represent solutions that are not whole numbers. Following the arrow to the right, we then transition to the integral solution. Here, the variables, now denoted as x, are all whole numbers. For example, x sub 1 equals 1, x sub 2 equals minus 1, and so on, down to x sub m, which equals 1. This perfectly illustrates the conversion from solutions with fractional parts to solutions that consist solely of integers. But how do we make this crucial leap? The question how, posed at the bottom left, highlights our central challenge. How do we effectively round or convert these continuous vector solutions into discrete integral solutions? To address that crucial question of how do we simplify our data for operations like rounding? Let's explore a powerful concept. This slide vividly illustrates the concept of projecting data into a higher dimensional space. On the left, you'll observe 3 red points. Notice how they're connected to form a triangle in a simple two-dimensional plane. An arrow then dramatically indicates a transformation taking place. And now, on the right, these same 3 points are beautifully re-represented, not as connected points, but as distinct spheres. We see a blue one, a gray one, and a yellow one, all within a 3-dimensional coordinate system. What this visual truly demonstrates is a fundamental principle. Data that might be difficult to separate or analyze when confined to a lower dimension can become much more easily distinguishable, and crucially, potentially linearly separable, when we intelligently map it into a higher dimensional space. It's almost like untangling a knot by giving it more room. Building on our discussion of how data can be separated and made more distinguishable, let's now explore a specific method, the two approximation algorithm. A core idea here is to randomly assign each vertex into one of 2 sets, say A or B. This process is quite similar to finding a random cut or partition within the graph. Now, take a look at the diagram below, which visually represents this very concept. You'll observe a graph featuring multiple vertices and edges. Notice the curved gray line. It beautifully illustrates a random cut, effectively dividing the graph's vertices into two distinct sets. And importantly, the edges that cross this gray line are precisely those connecting vertices from these different partitions. So, what will we do now? This slide immediately presents a crucial distinction. We are no longer in a graph space. Instead, we've moved to an asterisk vector space. Visually, you can see this represented by a three-dimensional coordinate system. Within this space, there are three distinct colored spheres, a blue one, a yellow one, and a gray one, each positioned as a unique point. So, continuing our journey through this fascinating vector space, where we've placed our unique points represented by spheres, we now ask, how do we meaningfully interact with them? This slide, aptly titled Random Cut by Hyperplane, gives us some powerful tools. Here, we'll encounter two fundamental definitions. Firstly, when working in a vector space, a hyperplane is uniquely defined by what's called a norm vector. This vector is absolutely crucial, as it's always perpendicular to the hyperplane itself, essentially dictating its exact orientation and position in space. Secondly, to precisely define a half-sphere, we use a hyperplane that does something very specific. It passes directly and squarely through the very center of the sphere. Let's bring this to life with the accompanying illustration. Here we clearly see a blue circle, which beautifully represents our sphere. Notice how it's being perfectly sliced right through its center by that vibrant yellow rectangular strip. That strip, in our example, twi's our hyperplane. And to really cement our understanding, observe the orange arrow extending from the center, perfectly perpendicular to that yellow strip. That, friends, is our norm vector, powerfully demonstrating the precise direction of this defining cut. Building on our understanding of hyperplanes and their ability to define a cut, this slide introduces the concept of a random cut by hyperplane. As its name suggests, the core idea here is to use a hyperplane to perform a cut. What's crucial is that this hyperplane's primary function is to partition into two distinct groups. Let's look at the illustration. You'll see a gray plane, which of course represents our hyperplane. A red arrow, conveniently labeled R, clearly indicates the normal vector to this plane, just like we discussed. Notice how perfectly this hyperplane divides the space. A dark red sphere labeled V_I is positioned neatly on one side, while a yellow sphere labeled V_J finds itself on the opposite side. This visual truly drives home how effectively the hyperplane separates different vertices into two distinct partitions, or groups. Following our discussion on how a hyperplane partitions vertices, we now delve into the concept of a torrandom time hyperplane. Given that there are, in fact, infinitely many such hyperplanes, a natural question arises. Out of these countless options, which specific hyperplane is the optimal choice for a particular solution to a semi-definite programming problem, or SDP? Here's the surprising answer. It doesn't actually matter which specific one you choose. You can simply pick any hyperplane, completely at random. This random hyperplane still serves its crucial function. It partitions all vertices into two distinct groups. And importantly, two vertices will be considered to be on the same side of a cut if their corresponding points land on the same side of this randomly chosen hyperplane. Alright, to kick off our analytical journey, let's begin by revisiting a foundational concept, the law of cosine. As you can see on the slide, we've conveniently set up a triangle for our demonstration. Vertex C is placed right at the origin, and vertex B is on the x-axis at point A, 0. Notice how the sides are clearly labeled A, B, and C, with C being the side directly opposite angle C. Below the diagram, we walk through the derivation of the law of cosine itself. We start, quite simply, by using the distance formula to find the length of side C. Once we expand those terms, we apply that fundamental trigonometric identity. Sine squared C plus cosine squared C equals 1, minus. And just like that, we arrive at the final familiar form. C squared equals A squared plus B squared minus 2AB times the cosine of C. For an even more detailed step-by-step proof, feel free to check out the Proof Wiki link conveniently provided right here on the slide. Building upon our understanding of the law of cosine, this slide now derives the cosine formula for the dot product, a truly fundamental relationship in vector algebra. Take a look at the diagram on the right. Here we illustrate two vectors, v and w, originating from a common point and forming an angle, theta, between them. Notice that the third side of this triangle beautifully represents the magnitude of the vector difference, v minus w. Naturally, our first step is to apply the very law of cosines we just reviewed to asterisk this specific triangle. Remember, it tells us that the squared magnitude of v minus w is equal to the sum of the squared magnitudes of v and w minus 2 times the product of their individual magnitudes, multiplied by the cosine of the angle theta between them. Now, here's a key observation. The squared magnitude of any vector, including v minus w, can also be expressed as the dot product of that vector with itself. So we have the dot product of v minus w with v minus w. When we expand this expression, applying the distributive properties of the dot product, it elegantly simplifies to the squared magnitude of v plus the squared magnitude of w minus 2 times the dot product of v and w. What happens when we equate these two different expressions for the squared magnitude of v minus w? It's quite straightforward. You'll see that the squared magnitudes of both v and w conveniently cancel out from both sides of the equation. And just like that, this direct comparison beautifully reveals the elegant cosine formula for the dot product. It states that the dot product of v and w is simply equal to the product of their magnitudes, multiplied by the cosine of the angle theta between them. This isn't just an equation. It provides a crucial and intuitive geometric interpretation of the dot product, linking it directly to the angle between vectors. As always, for a more detailed step-by-step derivation, please feel free to refer to the ProofWiki link provided on the slide. With our foundational understanding of the dot product now established, we can delve into its application in defining a random hyperplane. Our primary goal here is to infer times integral solutions, represented by x1 through xn, from a given set of asterisk vector solutions v1 through vn. The method involves picking a times random norm vector, rasterisk. We then cleverly use this vector to assign values to each x_i. Specifically, x_i is set to 1 if the dot product of v_i and r is greater than or equal to 0, and it's set to -1 if the dot product is less than 0. This approach effectively uses the random vector r to define a twine hyperplane *** that separates our solution space, allowing for a binary classification. And speaking of dot products, we should also note the crucial geometric relationship that we just covered. The cosine of the angle theta between any two vectors, v_i and v_j, is directly equal to their dot product. This is clearly illustrated by the diagram showing vectors v_i and v_j with the angle theta between them. Ultimately, this means all our x_i values are definitively assigned to either 1 or -1, entirely based on their position relative to this random hyperplane. Below this, we move on to an important times optimization problem times asterisk. We aim to maximize the sum over all pairs I less than j of a_ij times the term 1 minus the product of x_i and x_j, all divided by 2. This is, of course, subject to the critical constraint that each x_i must be either 1 or -1. The diagram on the right then illustrates a potential structure for these variables, perhaps showing x1 connected to x2, x3, and x4, which might represent a graph or dependencies within the problem, giving us a visual cue on how these elements could interact. Continuing our discussion from the previous slide, where we assigned x_i values based on their position relative to a random hyperplane. This slide zeroes in on a specific condition for an edge to be part of a cut within our optimization problem. Specifically, we define that times the edge connecting vector v_i and vector v_j is on the cut if and only if their dot products with our random vector r yield different signs. Think of this geometrically. The random vector r acts as a normal vector to a hyperplane, meaning an edge is cut only if v_i and v_j lie on opposite sides of this very hyperplane. This naturally leads us to a crucial question. What exactly is the cut probability of any given edge? Asterisk, asterisk. To help visualize this, let's look at the two illustrative diagrams below. In both, you'll see vectors v_i and v_j originating from a central point, with the angle theta between them, and our defining vector r, which creates the separating plane. On the left, notice how v_i and v_j are clearly separated by the plane perpendicular to r. This means their dot products with r would indeed have different signs, indicating that the edge between them flare on the cut. In contrast, the right diagram illustrates v_i and v_j residing on the same side of the plane. Here, their dot products with r would have the same sign, and consequently, the edge connecting them would not be on the cut. These visuals truly help us grasp the geometric implications of the cut condition, directly pointing us toward the challenge of calculating this probability for any edge. Building on our previous discussion, this slide focuses specifically on asterisk, how an edge gets cut by a random hyperplane, and crucially, what the probability of that event is. As we established, an edge defined by two vectors, v_i, and v_j, is considered to be on the cut if their dot products with a random vector, r, have different signs. Geometrically, this means v_i, and v_j, lie on opposite sides of the hyperplane, whose normal is r. So the key question naturally becomes, what is the cut probability of any given edge? In other words, what's the likelihood that a random hyperplane will actually cross between v_i, and v_j? Here, the orientation of each hyperplane is uniquely defined by its normal vector, r. Our diagram beautifully illustrates this concept. We visualize vectors v_i, and v_j, stemming from a central origin. Remember, vector r acts as the normal to our random hyperplane. Notice the angle between v_i, and v_j is labeled as 2 theta. This 2 theta actually represents the total angular separation. For the hyperplane defined by r2 asterisk actually cut the edge v_i, v_j. The vector r itself must fall precisely within this 2 theta angular range. Therefore, calculating the probability of such a cut is straightforward. It's simply the ratio of this specific angular range, 2 theta to the total possible angular range in 2 dimensions, which is 2 pi. This gives us the elegant formula, 2 theta / 2 pi, which handily simplifies to theta / pi, and there you have it. This theta / pi represents the precise probability that a randomly chosen hyperplane will effectively separate our 2 points, v_i, and v_j. Building directly on our last discussion about the probability of a single edge being cut, this slide now delves into the crucial concept of the approximation bound. First off, let's denote C as the total size of the cut discovered by our randomized hyperplane. The expectation that each individual edge, denoted as x_i, x_j, will be part of this solution is precisely what you see represented by that formula. This a_ij term essentially weights the contribution of each edge. So how do we calculate the expectation of C or EC? It's computed as a sum over times all times pairs I less than J, A_ij, dash. Remember, that's our weight for each edge, multiplied by the probability that the sign of the dot product of vector V_i, and our random vector R is asterisk not equal to the sign of the dot product of V_j, and R. This effectively means "v underscore I" and "v underscore j" are on opposite sides of the hyperplane. And here's where it gets really elegant. This entire probability term beautifully simplifies to "a underscore ij" multiplied by the 9-verse cosine time bought of the dot product of "v underscore I" and "v underscore j" all divided by "pi". What's fantastic about this simplification is how it directly connects the "a" and expected cut value to the very angle between the vectors "v underscore I" and "v underscore j" themselves. It's a very intuitive relationship. Now, let's quickly refer back to our diagram, which visually reinforces all of this. We still have our familiar vectors "v underscore I" and "v underscore j". The dotted line, as before, represents "r", our random vector, which is crucial because it defines our separating hyperplane. The angle "theta" here clearly illustrates the angular relationship between "r" and these two vectors. Remember, an edge is successfully cut if and only if "v underscore I" and "v underscore j" land on opposite sides of the hyperplane defined by "r". It all ties together beautifully. Building on the inverse cosine term we just discussed, this slide, titled Simulation, provides a crucial visual and mathematical insight, often applied in computational contexts. At the very top, you'll see a standard graph of the sine function plotted in red and the cosine function in blue. This serves as a fundamental trigonometric reference point. Below this, our main focus shifts to the graph depicting the arcsine function, shown as the solid red curve. Notice the dashed blue line representing a linear approximation or lower bound. The x-axis here spans from -1 to 1, which is the precise domain for the arcsine function. The specific point on the red arcsine curve is highlighted with a vertical yellow line, corresponding to an x value that results in a y value of 0.878. This visual representation is then formalized by the key inequality at the bottom of the slide. It states that the arcsine of x divided by pi is greater than or equal to 0.878 multiplied by the quantity of 1 minus x, all divided by 2. This inequality holds true for all x values between -1 and 1, inclusive. Essentially, what this demonstrates is how the arcsine function can be effectively bounded or approximated by a simple linear function within its domain, a truly useful technique in various simulation and computational algorithms. Building directly on our understanding of the arcsine relationship we just explored, let's now apply it to the core analysis of our algorithm. First, we'll denote C as the size of the cut found by the algorithm. Now, let's examine the expected cut size, E-core. As shown in the first equation, ECA is calculated by summing over all edges, mais guide, zal, the edge weight A underscore ij, multiplied by the probability that the random vector R separates the vectors V underscore I and V underscore j. This probability, crucial to our analysis, remarkably simplifies to the arcsine of the dot product of V underscore I and V underscore j divided by pi. Leveraging the inequality we saw earlier, this expected value, E's sake, is proven to be greater than or equal to 0.878 times a specific sum. A underscore ij multiplied by 1 minus the dot product of V underscore I and V underscore j, all divided by 2. What's profoundly significant about the entire sum term on the right? This quantity represents the optimal value of the semi-definite programming relaxation, or opt SDP. Therefore, our algorithm guarantees an expected cut that is at least 0.878 times the optimal SDP solution. Here's the powerful implication. Since the SDP relaxation value is a known upper bound for the true maximum cut, denoted as opt maxcut, this result further implies that our algorithm's expected cut is at least 0.878 times the actual optimal maximum cut achievable for the graph. This indeed is the famous approximation ratio for the max cut problem. Finally, on the right, The accompanying diagram visually represents the vectors v_i and v_j, along with the random vector r. The angle theta between v_i and v_j is also clearly shown, beautifully illustrating the geometric relationship that underpins all these probability calculations. Building directly on the analysis we just covered and the profound implications of that 0.878 approximation ratio, this slide brings us to our concluding remarks, highlighting the core achievements of this groundbreaking work. Firstly, the algorithm presented truly delivers a remarkable 0.878 randomized approximation for the MAX-CUT problem. This was not just a minor step. It represented a truly substantial leap forward, significantly improving upon the previous 0.5 approximation result. Even more profoundly, this research didn't just provide an algorithm. It pioneered the invention of a brand new, milestone technique that has had a lasting impact. And finally, here below, you can see the images of the brilliant researchers who developed and brought this pivotal work to life.